Thanks. Hello. Cool, mic's working. Thank you for joining. Yeah, just very quick introduction. My name is Dom. I work in the infrastructure platform team at Monzo. So we're the team that manage our Kubernetes clusters, basically. So very relevant me being here today. Today I'm just going to be outlining our sort of journey, auto-scaling Kubernetes. I'll start with some sort of definitions of cost optimization and stuff like that, and then just jump into sort of what we did before when we didn't auto-scale at all, how we're doing now, and sort of problems we faced along the way, because there's been quite a few. So just to start off with, optimizing compute costs. There's sort of three pillars of like how you can spend less and give AWS or your cloud provider of choice less money. These can be using less compute, which sounds obvious, but is key. Don't use the compute. Basically, you can either do that by dropping the size of services that your customers are using. You can alert when the service is at minimums and is sort of stuck there, and giving visibility to service owners as well of how much they spend. If they know how much they spend, normally they'll spend significantly less, you find. Committed spend is then sort of the next pillar. You can basically say to your cloud provider of choice, I'm going to use this compute, and I'm going to guarantee I use this compute, and if I don't use it, still charge me. This can be both reserved instances, where you reserve very specific instance types, or you can go for compute savings plans, where you basically reserve an amount of money you're going to spend every hour. The longer term commitments you do of these, the better. So a 1-year savings plan is worse than a 3-year savings plan, but obviously you're tied in for 3 years. Lastly is spot. So AWS call it spot. I don't know what it's called in other cloud providers, but they all have this. They have spare servers that they'll give you for slightly cheaper money, but with the caveat that they can take them away from you with 2 minutes notice. That's ideal for Kubernetes because everything should be disruption tolerant, and you should be able to kill nodes whenever you want. Measuring the cost compute efficiency is also key. It's fine to say you're being cost efficient, but actually measuring it is another thing. A key metric in platform teams you care about is cost per core. So if, say, you're spending 0.2 cents per core, and then you start using Spot across the business and that drives down, you can sort of measure how that's dropping down. It's a good sort of proxy metric to basically, if you're just using on-demand spend and not committed spend or Spot, driving down cost per core is really useful. It also has a sort of applying factor where the more compute you use as the business, as your business hopefully grows, the cheaper it's going to be, and you save more money over time. This is also important when you're showing teams how much they're spending. If you show teams exactly what nodes they happen to be running on, and it happens that one day they're on Spot and one day they're on demand, their compute spend can jump up 3 times for the next day. So instead what you need to do is show them the average money, because if they don't have control over running on Spot or not, there's no point just telling them, oh, you were more expensive this day because of something AWS side. The other side of this, in the sort of use less compute pillar, is just keeping an eye on wasted space. If you're slow to scale in, or you have unused capacity on your cluster, you're just wasting money that's sitting there, and AWS are probably getting it. So monitoring things like your CPU request utilization across your clusters, and also the speed of scaling. Here are sort of 2 graphs where you can see on the left, pretty good scaling, we dropped the amount of resource requests on our cluster, and our sort of cluster followed suit and quickly scaled in. On the right is one of the problems we faced during this talk that I'll outline a bit, where our scaling was very slow. All that green thing is just wasted money, basically, as we were paying for compute that wasn't getting used. So now that we know some stuff about cost, let's start with Monzo's Journey. Just to give a very brief overview of our Kubernetes landscape, we have about 3,000 microservices running on, we're focusing on a single cluster here, so we've not got hundreds of clusters or anything, all one cluster. 3,000 microservices. Alongside, we've got 3 Kafka clusters and 15 or so Redis clusters running here. There's also a bunch of other workloads. Pretty much everything in our business, except for 3 applications, runs on Kubernetes. The services themselves, they're scaled both horizontally via the HPA, vertically via the VPA, and we have this whole pre-scaling system. The reason we have a pre-scaling system is we get this peak at 4 p.m. when people get paid early at Monzo. And what this feature actually does is DDoS us at 4 p.m. every day. So we have to pre-scale the cluster to get ready for that DDoS, because people want their money dead on 4 p.m. They open the app and they just start causing problems. So that's what you'll see actually in this graph. This big drop is our pre-scaling going off sort of thing. And yeah, that runs pretty much every day. We also tier our services, so we've got 0 being the most critical, things like the ledger that calculates bank balances. That's a 0. And then 3 is the least critical. A good example is the service that tells you what emoji to send when you get a notification of your Monzo spend. That's a tier 3 service, although maybe that should be a higher tier. Our cluster itself, pretty large. We've got 20 to 30,000 pods, anywhere between 300 and 750 nodes, and that's about 10K to 25K CPU cores, depending on the day and the time of day. Now, a timeline here. We're going to start where we didn't autoscale at all. So for an autoscaling talk, that is a bit funny, but we were basically statically scaled. We would run out of compute, spend some more money to get some more compute, and then scale it in when we realized we didn't need that compute. We then moved to using the cluster autoscaler. This sort of dynamically scales up and down our cluster, and we'll talk through how we sort of set that up. And then the green bit here is sort of what most of this talk is going to focus on. We moved over to using Carpenter. We started using Spot to reduce that spend and that cost per core. And then we really increased and ramped up our Spot usage over time. Here is a bit of a spoiler of our Spot usage over time over the past 14 or so months. So you can see at the beginning when we were sort of trialing it out, this is daily spend sort of thing. So we were spending not much money on Spot, and as we've slowly increased it over time, the big spikes are sort of like end of months or like end of week sort of thing. You can also see a big dip actually in July where we started having some problems with Spot. So we quickly rolled back out of using Spot, investigated, made some mitigations, and then ramped it back up again. The sort of graph on the right is our new normal of using Spot across the cluster. So back to the start. We are going to, first of all, talk about PreCluster Autoscaler. This was not an ideal place to be. We had our priorities as a platform team, so we decided to not have any sort of autoscaling in our cluster. This obviously meant we wasted a bunch of compute. We had to set it manually, and we had a lot of toil work. We'd get an alert that fired in our cluster, in our alert channel, and it would basically say, we're running out of compute, add some more. And we would go into AWS, and we would add some more compute. And then we get an alert that says, you've got lots of wasted compute, remove it, and we'd go do that. As you can imagine, platform teams as autoscalers is not very efficient, and we quickly decided, let's optimize that. So we added the cluster autoscaler. The cluster autoscaler scales using autoscaling groups. If you're not in AWS, it will use whatever sort of cloud abstraction for managing pools of nodes you have. And all it does really is watch for unschedulable pods. These are pods that the scheduler has said, can I run them on the cluster? And it's determined it can't. So the cluster autoscaler says, oh, great, I'll give you a node. When it scales in, it's a relatively dumb scale-in as well. It basically terminates based on a percentage utilization of a node. We set it to 85%. So nodes with less than 85% CPU utilization would basically be killed. When we deployed Cluster Autoscaler, we spent a lot of work trying to make things disruption tolerant, basically. Once you start killing nodes all the time, rather than like once or twice a month, lots of teams come knocking at your door and say, hey, why are you killing my pods? And we sort of answer, your pods should be able to be killed, go away. Or, here's a link to documentation to make that better. That's probably what we said. We also had to provide a way to opt out for certain workloads. We run things, even including our OpenVPN pods in Kubernetes, and those basically will log people off VPNs when they get killed. So we needed a way to opt out of actually things being autoscaled as well. The graph on the right sort of shows a normal day in the view of the cluster autoscaler, so you can see the sort of quick scale in throughout the day, sort of stable throughout the hit, and then a drop down overnight, and we sort of quickly scale back in. However, we had some problems with the cluster autoscaler. First and foremost, speed. It isn't the fastest thing because it needs both the scheduler to have already looked at the pod and determined that it can't schedule it, and it also scales out nodes using autoscaling groups. And autoscaling groups take a bit of time to actually correct themselves and create nodes for you. Because of the speed, we also had to run quite a lot of headroom pods. So if, say, we take 10 minutes to add a node to the cluster, or 5 minutes probably, we want pods to schedule quicker than that. So we run a bunch of pods that are basically there to be killed. And these pods run with a low priority class. And when pods try and schedule, we evict the low priority class pods, service pods get scheduled, and then we scale out the cluster for those. This, in total, was about 8% of our cluster. So if you can imagine with a 20,000 core cluster, 8%, you're looking at a lot of wasted money just so we can make the cluster autoscaler not feel as slow as it is. Last of all, it isn't topology aware at all. It doesn't sort of pick nodes best for the pod that you're creating. All it does is just tell autoscaling groups to scale out. A big problem with this we had is when we had a sort of an edge proxy which needed to run one per node, so it was tolerant to sort of node failures. And the cluster autoscaler saw 50 pending pods and thought, oh, I can just add 3 nodes and it'll be fine. The problem is it added 3 nodes, it scaled 3 pods, and then we had 47 pods left that still needed nodes, and that repeated for about an hour. So it wasn't, because it's not sort of aware of Kubernetes topologies, it's quite slow in that regard as well. So introducing Carpenter. So we had a good opportunity here where we were migrating from self-managed Kubernetes to EKS. And as part of this, we decided we can deploy Carpenter in the EKS, slowly migrate workloads, and we can see how it performs as we migrate. Carpenter is a bit different, where instead of using autoscaling groups, it calls the EC2 API directly. What this means is it gets instant feedback from AWS if there's no capacity, and it can instantly retry and try various different instance types as well. It also preempts when nodes are being disrupted. So say AWS sends you an event that say this node is going to be terminated. Carpenter can first of all replace the node before killing the node that it's actually getting rid of. Because Carpenter actually includes the Kubernetes scheduling logic in it as well, it can pick the most optimal node for scaling based on both price, because it's instant price aware, and based on the pod itself. This, paired with us moving to a bottle rocket, meant that scaling went from sort of 5 to 10 minutes to about 2 minutes for nodes, so we could run much less headroom as well. As an example of Carpenter's scale-out logic, because it uses the simulations, you can basically provide lots of different node pools, and a node pool is basically a CRD that defines, here's the node, here's what it looks like, and here's the subnets and security groups it runs in. Carpenter can take the pod, run the scheduling logic, and first work out which node pools actually apply. Once it's worked that out, it can then prioritize the node pools based on both cost and custom weighting you can provide it. And then it can pick either, if it's an on-demand node pool, the cheapest on-demand instance for that workload, or if it's a spot, it uses this algorithm called price capacity optimized, which is like a mix of the cheapest, but also the most spare room that AWS have going for it. Here's an example of it compared to the cluster autoscaler. So because the cluster autoscaler takes about 2 minutes when telling the autoscaling group to scale out, it's much faster, but this is a lot more apparent when you hit an error. So cluster autoscaler basically round robins the autoscaling groups you give it. So if, say, you try and scale in a pretty unique instance type in one availability zone and AWS don't have capacity, you've told the ASG to scale that, you wait a couple of minutes, it times out, and then it tries it and tells another ASG. With Carpenter, you can try that instance, it can fail, and it can instantly retry and call that API again. This sort of makes Carpenter feel much faster than the cluster autoscaler. Another thing that both makes it feel faster and is a great benefit is its preempting ability. When you get a node termination event, Carpenter can first of all say, if this node didn't exist in the cluster, would these pods be able to schedule or not? Because it uses the Kubernetes scheduling code, it can pretty much work out what the scheduler will do before it's done anything. It can use that logic to then say, do I need a new node or not? If so, create the instance first, let the instance join the cluster, and then drain the node. And if not, just drain the node and let the scheduler handle things. This preempting is better for node termination events, but also when you get spot interruption events, you can sort of replace the spot node before the spot node's even gone away. Joined with the fact that nodes come up in less than 2 minutes, spot nodes can actually be replaced sort of before they're even taken away from you. So how did we set up Carpenter? With Carpenter, we needed both various node pools. So as mentioned, you can sort of customize where things can run with Carpenter. We had a default node pool. This was sort of where all microservices and pretty much everything lives by default. We had a low disruption node pool. Low disruption was where we ran things like Kafka and a lot more disruption intolerant workloads. And then we had some other node pools for more unique workloads, say our restricted node pool for security, or Prometheus, where we have some very massive memory instances to run Prometheus. The reason for different node pools here is a node pool can define things like a disruption budget, which tells Carpenter how fast it can do things like drift, replace, and drain these nodes. So for the default, we say 5% of all these nodes at once can go away. But with low disruption, we say one node at a time can go, which pretty much guarantees that we're never going to kill lots of the workloads running on low disruption at once. To set the topology for pods, so topology for pods is basically saying how you want your pods to be spread across the cluster. That might be things like I want a pod running once per host, or I want a pod running once per availability zone. We use an admission controller, which means we can sort of change that config dynamically instead of having to do redeployments when we want to change the topology of configured services. We also created a microservice that allows us to interface with parts of Carpenter. Notably, we have an RPC we can call that basically says, don't disrupt this node. We're in an incident and we're trying to investigate it. So we can tell Carpenter not to kill that node and we can just leave it hanging around. Carpenter itself as well implements a lot of the things that the node termination handler, which we were running in the old cluster, does. So it consumes some queues and it can handle both node termination and spot interruption events for you. You don't have to run a separate thing, which again makes all the preempt logic much, much, much better. Cool. So now we've got Carpenter deployed. Let's use some Spot. But the first question is, how much Spot? So balancing both Spot spend and your committed spend is quite tricky. If you use too much Spot and then AWS, Black Friday comes along, everyone gets compute from AWS and they take away your compute, you find you have a lot of disruption happening in a very short period of time. If you use too much commit spend, you basically might tie hands together and say, for the next 3 years, there's no point us optimizing our compute because we've already told AWS we're going to spend this many hundreds of pounds an hour. So trying to find your spot minimum is key. What we did is, as a sort of a minimum of our committed spend, was how much we use throughout the night, because that's the lowest peak during our day. We then took about 50% off that because we figured we probably have some compute optimizations in the future, and Spot was being quite stable for us. And we sort of picked a number where we were like, right, we're going to commit to this many hundreds of pounds an hour, and the rest we're going to cover with Spot. This is also then paired with us having to measure how much Spot we're doing and having alerts that fire when we've got too much just on-demand spend that isn't either Spot or committed. When using Spot, there's a lot of recommendations already on the Carpenter docs, which I recommend checking out, but you basically need to make sure you're having a wide range of instances. We use both the C, the M, and the R families, and CPU families as well. So we use the 5, the 6, and the 7 generation. We also use a variety of sizes for instances, so anywhere from 16 core to 128 core nodes, which gives us about 36 options for different nodes we can run in the cluster. The more diverse you are there, you're basically giving Carpenter more power because it can look at over the whole Spot market and say, what's the cheapest node I can launch at this point in time? If you limit it to just the 7 family, and then a lot of people started using on-demand for the 7 family, then you're not going to have a very good price on the Spot market. So the more loose you can be with your definitions, the better Carpenter will perform for you. One thing to note, which actually caught me out, is Carpenter doesn't handle Spot rebalance events. So it handles Spot interruption events for you, and it does consume Spot rebalance events. But it just consumes them and exports a metric about the fact it consumes them. It doesn't actually drain nodes and rebalance for you. So we actually had to run the node termination handler to consume rebalance events annoyingly for us. I'm hoping Carpenter add the ability to do that in the future as well. So how did we start using Spot? We started off where we just said, right, we're going to set a maximum amount of CPU cores that we can use that are Spot. This was about 5,000 CPU cores, and we set a higher weighted node pool that said, pick this node pool first, fill it up, and then just go to on-demand. This was good. It allowed us to start trialing Spot without having to make too many changes. But very quickly, as we ramped up that maximum, we realized it was quite inflexible. We then moved to using Spot and on-demand in one node pool and on-demand in the other. The reason you want on-demand as a fallback in your Spot node pool is if it's a Spot-only node pool and you have a pod that is affixed to that node pool, Carpenter can't fail back to on-demand when you run out of Spot instances. So you need to make sure Spot and on-demand is an option, even if Carpenter's always going to pick Spot as the cheapest option. We then realized it was crazy just having an on-demand node pool, so we instead moved to having basically one big node pool with Spot and on-demand. This really simplified Carpenter's logic because it didn't have to sort of work out across loads of node pools. And the less node pools you have, the quicker the simulations are for Carpenter as well, which I'll get into in a bit. Lastly, once you're using Spot, you want to make sure you're always using the committed spend that you have in your AWS account. You don't want to be paying AWS hundreds of pounds an hour for your committed spend and not using it. So what you can do is create a node pool called committed spend, which is on-demand only, and set a maximum amount of cores there. And you can basically fill up this bucket of committed spend and let Carpenter then go to Spot when it's available. Having this has been very useful because we can sort of very quickly and easily adjust the committed spend node pool based on that and then we can default to spot when it's available. We actually, for a while, had the committed spend node pool down to 0 as we were using more on-demand in other parts of the business. And since then, we've sort of moved it a bit up to make sure we're constantly using that commitment. Having alerting on using the commitment is very important as well, because you just don't want to be wasting that money. So, is that it? Is everything great with Carpenter? Here's the problems with Carpenter slide. So, as you can imagine, 3,000 microservices, 30,000 pods. Carpenter is running the scheduling logic, not just once for a single pod, but it's running it for every node to see if it can disrupt and consolidate nodes. It's running it anytime it launches a node, and it can very quickly get very, very slow. This was the first problem where we found Carpenter would basically get stuck trying to scale in our nodes. And the graph I showed at the beginning where we had like thousands of pounds of wasted spend was because of the fact that our scheduling logic was slowing down. The other issue is Spot. We were using too much Spot at times, and we actually found that we would get so much disruption that Carpenter couldn't handle it. We thought at the time it was because of the scheduling logic, but after we fixed that, we realized that our PDBs across all of our pods were basically blocking Carpenter from gracefully draining the rest of the nodes. So we had sort of 50 to 100 Spot nodes going at one time, and Carpenter would pretty much quickly stagnate trying to evict it because the pods were like, I can't be evicted. I've got a pod disruption budget, unaware that their node was going away in 90 seconds anyway. I really wish for that we had a PDB that was like for friendly times and PDB for eviction times. But lastly, the scaling behavior of Carpenter is a bit weird because when it scales in, it ignores like soft topology spreads. Say you have a workload that's balanced across availability zones. When Carpenter wants to get rid of some nodes, it picks the most expensive node first. If you ever looked at the spot market, you'll know that like availability zone spot prices really differ, and there's normally one that like everyone prefers. So Carpenter kept getting rid of nodes in availability zone A. So we'd wake up in the morning and find that we actually had no pods running in availability zone A for certain services, because Carpenter had decided to just get rid of those because they were the most expensive. The fix for that is using a hard topology spread rather than a soft one. So, optimizing scheduling simulations. PodTopology spreads is I would say relatively new. It's like in the last 15 versions of Kubernetes, but it's a relatively new way of sort of spreading pods across failure domains. These are significantly more efficient than pod and node anti-affinities. The graph on the right sort of showcases this, where the top one is our P99 scheduling timings for Carpenter's simulation. When we move from affinities to topology spreads, they're still like for like, the exact same logic. Our P99 went from about 50 seconds to 3 seconds, and our P90 and our P50 dropped as well, like massively. This is quite a foot gun when you have quite a complex cluster. It doesn't really matter when you've got a small cluster because things are quick enough anyway, but it really like caught us out at times. The other thing, as I mentioned before, is the less node pools you have, the better. Carpenter can pick the best instance for you, so don't give it lots of complex node pools. Keep it simple so Carpenter can make the best decision instead of you trying to program it into Carpenter. We've sort of overcomplicated some of our node pools at times, and it's really slowed down some of the processing. The last thing is I'll mention a bit more detail later on, but having a mutating webhook that sets like a node selector is much more efficient than trying to use topology spread for using Spot. So, as an example, Carpenter's docs recommend that you can set a topology spread of between Spot and on-demand nodes that says, I want a balance of 50% for both. This is fine, but paired with 2 other topology spreads, the simulations that Carpenter has to run get so complex that it really slows down. So instead of that, we have a mutating webhook that can basically say, for 50% of the pods for this service, inject a node selector that makes it run on Spot or not, which is miles faster for simulations. Again, it doesn't matter unless you've got a very large cluster. When you're sort of starting out, don't start with the complexity, but when you need to drive these efficiencies, that's a great way of doing it. So, our Spot termination issues. I showed this graph before, and you can see this big dip for about 15 days when we basically quickly pulled out of using Spot for some of our tier 0 and 1 services. We saw basically very large spikes of 50 to 100 terminations in a 5-minute window. This took a lot of energy for Carpenter to compute. It got blocked by PDBs, and it basically meant that thousands of pods were ungracefully terminated. Our service measurement retries sort of hid the issue, and it wasn't really noted, but we sort of saw a big dip in our connection errors. The biggest mitigation against this, aside from making sure your PDBs aren't too restrictive, is consuming those Spot rebalance events. AWS send you an event that say, this node is more likely to be terminated than it was when you launched it. Maybe you should get rid of it. If you don't action that, it's pretty much likely going to be terminated in the next couple of hours anyway. So handling those events and terminating them are really key. Lastly, just to talk about the PodTopology Webhook a bit, as you can see in this slide here, the speed in which we were able to stop using Spot was only possible because we had this webhook where we could basically configure it and say, for tier 0 and 1 services now, inject in the information that says don't use Spot or on demand for 50% of the use cases. This meant that instead of having to do deployments and update manifests across everywhere, all pods that got created, and we just had to do an eviction, would then move off of Spot and onto on demand. The nice thing is when a Spot termination happens, it also terminates things for you, so a pod gets recreated and gets balanced. This webhook has also been a bit of a superpower in terms of the ability to sort of extend what it can do in the future. We could make the topology webhook aware of our committed spend and use more on demand when we know committed spend is dropping low, for example. Having this has meant that our Spot, everything we've done with Spot has been much quicker to experiment with and to change things and see how it goes. It's also acts as a single source of truth for our topology config. Before, it was in our deployment pipelines, in the manifests for services that got deployed, whereas now it just lives in this service. And finally, in conclusion, just to sort of drive home some key points, moving to Carpenter meant we could really increase our cost optimization and flexibility. The key thing really with Carpenter is because it's you can have such different node pools, we're not just auto-scaling our default microservice node pool, we're auto-scaling our Prometheus node pool and our security node pool as well, which it just means everywhere has auto-scaling rather than just what you configure the cluster autoscaler to do. Spot is great, but you can really overuse it, and you notice when you come to time of the years like now, where other people are using lots and lots of compute, AWS have less spare capacity, and you get lots of termination events. Another key thing is alerting on that. We didn't have any sort of info-level alerts that say, we've just had a big spike of Spot interruptions, and we were just like, why have all these pods showed up from nowhere? So having that alerting is very key. And lastly, allowing quick experimentation and quick rollbacks when you're doing these sort of changes for both like Spot and on demand is really important. If we weren't able in an instant to just say, right, move off 50% of Spot, we probably would have had to done a slower rollback and then be more careful as we rolled it back across the business. Cool. That's everything. If you have any questions, I can answer them, maybe.